In the previous video, we talked about the inner product, the inner product space, and all those things, right? And we know that inner product is follows the property of positive definiteness. Now we are going to see the positive definite matrices. But before that, let us try to take the idea, or let us try to move this idea from the inner product towards the matrices. So for that, again, we are looking the vector space with respect to some basis B. So let us suppose that we have a V, an n-dimensional vector space, and B is a ordered basis. It's a basis, right? And let us suppose this is all the basis vectors are these one. Okay, so these one, fine. And the inner product is defined over this particular vector space. We have defined in some way, right? It may not be the dot product. So since every vector in this vector space V can be represented as the linear combination of basis vectors, so we can write them all like this. Now if we are going to find out the bilinear mapping or the inner product value of these two vectors, we can write it like that because it's a bilinear mapping. So you take y to be same and you expand your x vector with this particular thing, and since it is left linear, you can express it as xi cap omega b I y, and so on and so forth. So you can write like that, and again in the next step, or again if you simplify with the right linear linearity property of the bilinear mapping omega, then you will find you can write it like this particular thing, this particular expression. So if you see it, then the idea is that you can actually represent this particular thing as a matrix multiplication, because all these things can be written as vectors. So this x cap can be written as vector, yj cap can also be written as vector, and this omega can be written as a matrix like this. Once you do that, we are now able to write any omega xy, any bilinear mapping, or any inner product like x transpose a y. So ultimately, even if it is a dot product, you have this A to be identity matrix, and if it's not a dot product, you will get some matrix A there. If it is a bilinear mapping, some matrix A will be there. Now, we say that it's a positive definite inner product. So omega is representing the positive definite inner product. So in that particular case, that this omega xy, if I pass on the same vector, it should give me positive value for all non-zero vectors, right? So that is the definition of the positive definiteness of the omega of the inner product. So let us see that the symmetry of the inner product makes asymmetric. That is very correct, because inner product is symmetric, so asymmetric. Positive definiteness, so let's talk about positive definiteness. So positive definiteness says, because you take omega x vector, now this is equals to x transpose a x. So that comes out with the thing. So the same thing which we are looking in omega this way, the definite positive definiteness, in the definition of the positive definiteness of the inner product, actually results in the matrix form like this. And with this, we say the definition of the positive definite matrix becomes this one, that for every x, every non-zero vector x, x transpose a x, if that comes out to be positive, then we say the A is positive definite symmetric, positive definite matrix. So that's the idea. So so one thing you can notice, that something, if this particular thing is true for every non-zero element of non-zero x vector, which essentially means the determinant of A will not be 0, will not be 0, because it will be 0 if and only if this, a lot of factors actually goes to 0, actually takes to 0, right? So which is not possible without x to be 0. Okay, so the null space has to be, so which also means the null space, okay, fine, which means that null space has to be 0. Now let us try to look at two different matrices, and we see that, or we want to see whether uh, what is the case, how we can see that. Okay, so let us see. In the first matrix, we can actually transform it like this one, which can be written, so this x transpose a1x can be written as this, and since these two terms, both the terms are square terms, it has to be positive for all x is not equals to 0, right? And hence it is positive definite. Now looking at this particular expression, this comes out to be this one. So if x2 square becomes larger than the 3x1 plus 2x2 whole square, then it may go negative. So sometimes it may be positive, sometimes some other times it may be negative, and this particular matrix or the bilinear mapping inner product with respect to this matrix is not positive definite. Then there is something a little bit different, that is positive semi-definite. Now the positive semi-definite allows you to have zeros even if x is not 0. So even if x is not 0, even then if x transpose ax comes out to be 0, it is okay. Then those matrices are called positive definite, semi-positive definite matrices, right? So many of the vectors may converge or may point to 0, right? So even if the x vector is non-zero, x transpose ax may come out to be 0, and then it is called positive semi-definite. And definitely, if you are talking about a positive definite, symmetric positive definite matrix, x transpose ax is positive for all non-zero vectors, and all the standard basis vectors are non-zero vectors. If I say that, then 1 0 0 0, if I take the vector 1 0 0 0 and its transpose, if I take and I do that x transpose ax, I'll get only the diagonal element. I will get only the diagonal element, and if I get the diagonal element, which means all the diagonal elements has to be positive, for has to be positive, right? So that's the that is one of the result that comes out from the positive definiteness. So if a matrix is positive definite, its diagonal elements has to be positive. So in the next, we are going to talk about lengths and distances. Uh, the lengths and distances are, again, they will give you the sense of direction, because they can reduce if you know the length, if you know the distance, you can find out the symmetricness, or you can find out the similarity between the two vectors. So in the next video we are going to talk about lengths, distances, and possibly the angle between the two vectors. The angle between two vectors is also a very important idea in machine learning, because um, angle tells us the similarity between two, or the directional similarity between the two items. So thank you for now, and we are going to discuss length, distances, angles in the next video.